All right, so now we're going to use mathematics and we're going to learn something. Why? Well, the fact that light does not obey these equations is going to lead to something phenomenal, right? Okay, so we got to explain this. Here we go. Okay, all right, so what did we just learn? If frame S prime is moving relative to frame S, the speed of light in S, okay, sorry, start over. If you're throwing a baseball from a moving car, right? So in other words, if frame S prime, the car, is moving relative to frame S, the highway, then the speeds are different. No kidding, right? That's what it means, no kidding. I mean, it's obvious, right? Okay, however, it doesn't work with light, right? Well, let me back up, sorry, I forgot. Okay, so if the speed in S is not equal to speed in S prime, that means delta x over delta t in S is not equal to delta x prime over delta t. No kidding, right? Because that's the definition. Okay, so that's fine, we agree with that. But again, it doesn't work with light. No matter what reference frame you're in, everybody measures the speed of light to be the same speed. So u equals u prime. What does that mean? It means delta x over delta t, I guess, says that delta x prime equals delta t, right? I mean, doesn't this imply this? Well, I don't know, because, wait a second, how can this possibly be true? Is delta x equal to delta x prime? No, come on, right? Here's delta x prime, here's delta x. So that's insane, right? This is not equal to this. So how could that be equal to that? So you figure it out. So pause your video and figure out how this can be true, because it is, right? This has to be, well, and we've got to fix this, of course, but this is true. So if this is true, how can we fix this to make it true? So pause your video and figure it out. Okay, this is true, right? The speed of light in any reference frame, the same, right? Speed of light in this reference frame equals speed of light in that reference frame. So we have to look at this, right? Because, but here's the thing. We know that delta x is not equal to delta x prime. They're completely wacky different. So how can this be true? The only way it can be true is what? If this delta t here is not the same as the delta t there, right? It's the only way, okay? So what we're saying then is that if this is true, then maybe this is true. In other words, we're being kind of radical. We're saying that delta t is not equal to delta t. I mean, we're saying, yeah, delta t is not equal to delta t prime, right? This is not equal to that, so this can't be equal to that, because this has to equal this, right? All right, but we've always grown up thinking delta t is delta t, right? Who cares what reference frame you're in, Like I said earlier, somebody sneezes, you measure the length of the sneeze, I measure the length of the sneeze, I don't care if I'm in a jet, whatever, it's 2 seconds for a long sneeze, or I don't know, half a second or something like that, right? We've always thought delta t was the same. But now we're saying, my gosh, maybe it's not the same, Maybe it's not the same. So delta t is not equal to delta t prime. So that means that time is relative. There's my time, there's your time. All right? We're talking about the time for one, like a sneeze or I don't know, a clap or something. We're going to get different times if we're in different reference frames, and we're both right. So that's weird, right? Delta t is not equal to delta t prime. So I love this. The more I think, the more confused I get. So if you're feeling like that, that's okay. Don't worry about it. Okay, so time is not absolute. It's relative, just like size. Okay, so just keep that in your head. We'll get back to it. Now we want to talk about something called an event, because it's crucial to the whole relativity. What's an event? This is what we mean by an event. An event has space-time coordinates. What's space-time? Space-time. So space is x, y, z, right, the position, and time is t. So an event has space-time coordinates x, y, z, t in frame S, and different space-time coordinates x prime, y prime, z prime, t prime in frame S prime. Okay, whoopee! All right, so that's fine. So here, what's an event? And this is an important question, right? So just guess if you haven't read it. What's an event? Is it what really happens, or is it our perception of what happens? Now think about it. This is physics. So what's important? What really happens or what we think? You know, who cares about our perception, right? An event is what really happens, okay? That's the important thing. So an event has a unique set of space-time coordinates in every reference frame. And it's what really happens, not necessarily what we perceive. And we'll talk about that, don't worry. All right, here's a question for you. Without going outside, how do you know the sun is still in the sky? How do you know? So some people say, well, you look out the window and it's still light outside. Wrong. You don't know. What do you mean you don't know? Well, it takes light. Okay, so here's the sun. This is not the scale. There's the sun. There's the earth. So it takes light about 8.3 minutes to travel from the sun to Earth. So if you had a filter and you look at the sun, what are you really seeing? You're seeing what it looked like 8.3 minutes ago. All right? So for all you know, it could be gone right now because you're only seeing it, 8.3 minutes ago. All right? So that's what I mean. There's your perception and there's what really happens. Okay? Okay, let's kind of beat this to death a little. A carpenter is working on a house 2 blocks away. You notice a slight delay between seeing the carpenter's hammer hit the nail and hearing the blow. At what time does the event hammer hits the nail occur? So think of what I just said about the sun and all that. So pause your video and figure it out. By the way, what travels faster, light or sound? Light by far, right? I mean, remember, speed of light is 3 times 10 to the 8th meters per second, right? That's c. Speed of sound is like 343 meters per second. So, I mean, sound is super slow compared to light. Okay, so let's vote. What do you say? Well, you're going to see the hammer hit the nail first, and then you're going to hear the sound, right? And it takes time for that light to reach you. Not very much time, but it's going to take some time. So at what time does the event hammer hits the nail occur? Very slightly before you see the hammer hit, right? So the hammer hits, then slightly after that you see it, then slightly after that you hear it. We used to live in Illinois, and they built a brand new stadium in Chicago for the Chicago White Sox baseball team. And when they opened it, they gave out free tickets to a baseball game. But they were all, really the crummy tickets, right? Really way up high, so you're really, really far away from the field. And it was kind of funny, I remember, because, you'd see the batter hit the ball, and you'd see it, and then it almost seemed like there was like a half a second, I don't know, or maybe a second, I don't remember, but it just seemed like there was a really, really long delay until you finally heard it. I mean, it was so incredible. But anyway. Okay, let's see. Okay, we're going to keep more of these questions going. Ann and Bill are standing 1,200 meters apart and are facing each other. A firecracker explodes 900 meters from Ann, and of course 300 meters from Bill. And she sees a light flash at t equals 5 microseconds. So that's when she sees it. So what we want to ask is when, at what time did the explosion actually occur? And you want to use this. So you know how I always say that speed of light is 3 times 10 to the 8th meters per second, or 300,000 kilometers per second? Well, here's another one, which is nice for these kind of problems. Speed of light is 300 meters per microsecond. Okay, so use this and figure it out. So pause your video and figure it out, please. Okay, so how long would it take the light from the firecracker to reach Ann? Well, it's 900 meters, right? So distance equals speed times time, right? And so the time is the distance over the speed, which is the distance over the speed of light. So the x is 900 meters. The speed is 300 meters per microsecond. So what's that? 3 microseconds. Hopefully you didn't have to do all this. Hopefully you just do it in your head, right? I mean, right? You know? Okay, but anyway. All right. So here's the question. I didn't ask that. It said, what time did it occur? So it takes 3 microseconds to reach her. But she said she saw it flash at 5 microseconds. Well, then when did it occur? It occurred at 2 microseconds, right? It occurred at t equals 2 microseconds, and then it took 3 microseconds to reach her. So according to Ann, it reaches her at 5 microseconds. Make sure I understand that. Okay, now here's the question. Are seeing the flash and firecracker explodes the same event? If not, which is more significant? Now remember, the event is when something actually occurred, right? It's not our perception. So are seeing the flash and the firecracker explodes the same event? No, of course not, right? Of course not. She saw the flash at 5 microseconds, but that explosion took place at 2 microseconds. Okay? So they're not the same, but what's more significant? When it actually occurred, 2 microseconds. Okay, right? So when it explodes, okay? Now, okay, so we know it actually occurred at 2 microseconds. So now the question is, when did Bill see the flash? So pause your video and figure it out. Okay, so it actually occurred at 2 microseconds. How long does it take to go from here to here? Well, it's 300 meters, so it takes 1 microsecond. So it actually occurred at 2, takes 1 microsecond to reach him. So he's going to say, I saw the flash at 3 microseconds. Okay, now it's getting even trickier. Maybe, I don't know if it's trickier. Ann and Bill are still standing 1,200 meters apart, facing each other. Firecrackers explode. Now this is different, right? Firecrackers explode 300 meters from the front and back of Bill. And Bill, using an extra set of eyes in the back of his head, sees the 2 flashes at the same time, okay? So these are same distance. He sees the flash same time. According to Bill, were the 2 explosions simultaneous? Now think back to what we learned about simultaneous. So were they simultaneous? Well, the same distance, right? They travel at the same speed. The light travels at the same speed. He saw them at the same time. So yeah, they're simultaneous, right? Because it took 1 microsecond to reach that, 1 microsecond to reach that, because it's the same distance. He saw them at the same time. So yes, they're simultaneous, according to Bill. Okay, according to Anne, were the two explosions simultaneous? Anne is very intelligent. Now notice, the question says, were they simultaneous? It doesn't say, did she observe them at the same time? It doesn't say that. It says, were they simultaneous? And she's super genius. Doesn't have to be a super genius. But. So what's the answer? Pause your video. Figure it out. Well, come on. Do Anne and Bill share the same reference frame? Yeah, they're not moving relative to another. So if something is simultaneous to Bill, it has to be simultaneous to Anne. So the answer is yes. Okay, one more. Anne and Bill are still standing 1,200 meters apart, facing each other. Again, the firecrackers explode 300 meters away from the front and back of Bill. Now this time, Anne sees the two flashes at the same time. Anne and Bill are both very intelligent. According to Anne, were the two explosions simultaneous? Again, it doesn't say, did she see them at the same time? It says, were they simultaneous? Well, what do you think? So pause your video and figure it out. Okay, the answer is no. Of course, because look at this one, the light travels less distance than this one. Agree? So in order for Anne to see the light at the same time, this one has to go first, and then this one, and then the light hits her at the same time, right? Okay, so the explosions were not simultaneous because the light for one of them traveled longer than the light for the other one. According to Bill, were they simultaneous? You don't even have to think. Bill and Anne share the same reference frame. So therefore, something is either simultaneous for both or not simultaneous for both. So if they're not simultaneous according to Anne, they're not simultaneous according to Bill. Simple as that. Okay, so what's the whole moral of all this stuff? Why do we have to do all this? The perception of an event is not the event itself. All experimenters in the same reference frame agree as to whether or not two events are simultaneous. We already talked about that, by the way. That's okay. It's a little review never hurt. But the thing is, in practice, the experimenters, they have to calculate the time delay effects to turn their perceptions into measurements of the space-time coordinates, okay? And so we're going to assume that people are smart enough to do that. You know, just like Anne and Bill, right? You know, they were smart enough to figure out, they knew that the speed of light was 300 meters per microsecond, so they could figure out when the event actually occurred. Okay? All right. Okay. Okay, what we want to talk about now is the speed of light. Okay, I indicated earlier that the speed of light is constant, and now I'm going to go into much more detail. Okay, so we learned about this in the previous chapter, the electromagnetic wave theory of light. Remember when you shake a charged comb? Okay, every accelerated charge object creates a disturbance in its own electromagnetic field, a wave, right? Oh, disturbance of a medium, a wave, which spreads out throughout the field at 300,000 kilometers per second. Light is such an electromagnetic wave. So we made a big deal about that, right? This came from the Maxwell equations. Every form of light travels at the speed of light. And it doesn't matter if you're talking about low-energy radio waves or visible waves or high-energy light, gamma ray light waves. Every type of light travels at the speed of light. Now they can have different frequencies, different energies, different wavelengths. We don't care. Well, we do care because this still has to be true, right? You know? So it can be any frequency and wavelength as long as that product equals the speed of light. By the way, when we say things travel at the speed of light, that's in a vacuum, okay? In a vacuum. All right, so The Maxwell's equations predict that light travels at one speed, the speed of light, 300,000 kilometers per second. So, you can say that's a fact, right? It's a fact. All right? Okay, so this is a logical argument that Einstein used, and it's very important that you understand this logic. All right, so here we go. So we start off with the principle of relativity. The principle of relativity says the laws of physics, which includes mechanics and electromagnetism, are the same in all inertial reference frames. Got it. Now, give me one law of physics relating to this, the speed of light. So a law of physics from electromagnetism, from Maxwell's equations, is that the speed of light is constant. Everybody measures the speed of light to be 300,000 kilometers per second. Doesn't matter how fast you're moving, doesn't matter how fast the light's moving, everybody measures speed of light to be speed of light, right? And Maxwell's equations say that. The speed of light can only travel at that speed, okay? So take this, laws of physics are the same in all inertial reference frames, add it to this, speed of light is constant, and what do you get? You get this. Therefore, the speed of light has to be constant in all inertial reference frames. Just as logic, right? Just good old logic. I mean, it seems crazy, right? When you think about it, but it's just logic. So make sure you understand this. You got to think about it. You can't memorize. You got to think about it. That's what's hard about relativity. You can't just memorize. You got to think about it. Okay, so make sure you understand that. Okay. All right, so I'm just, saying this over and over again. So the speed of light is constant regardless of the observer's motion, regardless of the light source's motion. Everybody in inertial reference frame, moving frame, I don't care, as long as it's not accelerating, right? Everybody measures the speed of light to be the speed of light. I don't care how fast a rocket is going. I don't care if it's going toward you or away from you. I don't care. Everybody's going to measure the same speed from that light from the rocket. Everybody. If the rocket is still, if it's moving, I don't care. Everybody measures the speed of light to be the speed of light. Completely insane, right? But that's how nature works. I already talked about this, right? So the runner measures the speed of light coming from the flashlight to be the speed of light, and the stationary observer measures the speed of light. I don't care how fast the train is going. I don't care what direction the train is going. I don't care how fast the runner is going. I don't care what direction the runner is going. Everybody measures the speed of light to be the speed of light, period. Whew. Okay, now you say, Brother Weber, that sounds insane. And I say, yeah, of course it does. It sounds completely insane. Well, let's see the data, right? This is physics, data, All right, so this experimental evidence. So this is Fermilab. I used to work there. This is 40 miles west of Chicago. This is a particle accelerator. So this is 4 miles in circumference, and you get protons going really, really fast. And you just smash them into other things, and you learn about what makes up matter and all sorts of fun stuff. So why do I talk about this? Well, when you're doing experiments with relativity, you want things to go nearly the speed of light. Well, we can't, we don't have rockets that go nearly the speed of light. We don't have anything except here. These protons go at nearly the speed of light. So you can do these relativity experiments at particle accelerators. Pretty much, well, okay. All right, so let's talk about it. Okay, so here's an experiment done a long time ago. So this experiment involves something called a pion. So a pion is a subatomic particle, and it doesn't live very long. So we use the word decay. When it dies or ceases to exist, it decays. So there's many ways that pion can decay, but here's one way. So a pion, a neutral pion, can decay into 2 photons. Remember, a photon is light, a particle of light. Okay? And how fast does a photon move? Speed of light. So it's light, right? It's like, what color is an orange, Orange, okay. Okay, so this was an experiment done in Switzerland in 1964, a long time ago. And so what they did, they got pions going to nearly the speed of light. Come on, that's nearly the speed of light, right? 0.99975 times c, that's the speed of light. Close enough, right? Okay, so they accelerated these pions until they got to this speed. So just think of these pions going at this speed. And remember, they don't live very long. And so, you know, the pion's moving along, and then it dies, right? So it decays into 2 photons. And so let's just say that one of the photons goes this way in the same direction that the pion was going, and the other one goes in the opposite direction. So here's the question. What is the speed of the photon on the left? So what's the speed of the photon? So this photon. So I want you to, all right, so let's look at it 2 ways. So first, let's answer the question according to Galilean relativity, or Isaac Newton, you know? So let's just make it simple. Let's just say that this pion was going at the speed of light to the right, and then it, you know, like, okay, let me demonstrate. So I'm the pion, so I'm going at the speed of light, oh close enough, right? And then I decay in 2 photons, right? But remember, when I decay, you know, I'm moving, right? I'm moving when I die and when I'm shooting off the 2 photons. So what we want to know is the speed of this photon. So please answer this question. What is the speed of that photon according to Galileo? So pause your video and figure it out. Okay, so what would Galileo say? He'd say, well, come on, this thing is going speed of light that way. Then it emits a particle going speed of light that way. You know, speed of light that way plus speed of light that way is 0, right? So Galileo says 0. You know, it's just like if you're in a truck going 100 miles per hour this way, and you shoot out a baseball going 100 miles per hour that way, and there's no air, what's it going to look like? Straight down, right? There's a video about that, by the way. Okay, so Galileo says 0. But what does Einstein say? In other words, what really, really happens? Now remember, this pion's going nearly the speed of light this way. And then it shoots a photon going that way. So, you know, I mean, this kind of makes sense, but it's wrong, right? What does Einstein say? Everybody measures the speed of light be the speed of light. So there it is. Right? So when people measure the speed of this guy, it's going speed of light. If they were to measure the speed of this photon, what would be the answer? Speed of light. Insane, right? But it's true. Okay? Galileo would say this would be moving at twice the speed of light, right? If you say that's going at the speed of light this way, and then this goes speed of light, Galileo would say twice speed of light. It's wrong. Okay? Einstein is right. Everybody measures speed of light be the speed of light. So there's data for it, right? There's data for this. Okay, and there's much, much more, but I'm not going to get into it. Let's review. So if you want to really be picky, this is the speed of light. 3 times 10 to the 8th, close enough, right? And why do they use c? Well, this is somebody's opinion. C is this, which is Latin for speed. I don't know if that's a tail or what, but anyway. So that's speed of light. Now remember, what did we talk about at the very beginning? Remember that question I said about I'm passing you on H1? And I said, you know, there's reference frames, and when you say what the speed of something is, you have to say relative to a reference frame. Remember that? Well, guess what? This is the speed of light with respect to what? With respect to any inertial frame you like. The speed of light is constant, period. No discussion. Okay? Doesn't matter how fast you're going. Doesn't matter how fast a flashlight or headlight or whatever's going. Everybody measures the speed of light to be the speed of light. End of story. And again, this is super important that you understand this logic. The principle of relativity says laws of physics are all the same in all inertial reference frames. Here's a law of physics. Speed of light is constant from Maxwell's equations. Therefore, just logically, the speed of light has to be constant in all inertial reference frames. It's logically tight, right? It's a perfect argument. I mean, it seems crazy to us from our experience, but it just seems crazy to us because we never go nearly the speed of light, so we don't have any experience really, you know. Okay, well, here's another one. Oh my goodness. Special relativity, one fundamental premise, the principle of relativity. If you accept the principle of relativity, you have to accept the fact that the speed of light is constant. And this has been shown to be true, and this has also been shown to be true. So there you go. Whew. Okay, let's see. Do I want to do that now? Yeah, let's quit.